There was a universe. We'd just begun to discover that distant galaxies have stars in them.
A universe existed. We are only now learning that stars exist in far-off galaxies. Our understanding of the cosmos has already been altered by the James Webb Space Telescope. However, a scientist who won the Nobel Prize is now making a startling assertion. They contend that the telescope could have found a completely new universe, a finding that would fundamentally alter our understanding of time and space. Scientists have been speculating about the possibility of other universes for years, but this discovery could be the big break they've been looking for. Let's investigate its meaning. The James Webb Telescope is now available. Astronomers and space fans across the world are giddy with anticipation over the James Webb Space Telescope, commonly referred to as JWST or just Webb. Long-held aspirations to probe further into the early cosmos have been dashed by the size and design constraints of older telescopes. This is altered by the Webb telescope's far higher sensitivity to infrared light, which is essential for observing far-off, dim objects. As space expands, light from these far-off places stretches and moves into longer wavelengths, which are best seen in the infrared spectrum. This telescope specializes in just that, and it accomplishes it with amazing clarity. Its introduction was a huge undertaking that required decades of planning and construction. Its equipment and mirror segments were developed by scientists and engineers from several nations, guaranteeing that it could view minute details in the furthest regions of the universe. Once in orbit, JWST started returning data that immediately attracted attention since it went above and beyond predictions, revealing characteristics that some models predicted would not have been apparent at that time. It saw galaxies that were too large and well-formed for their era of existence. The initial astonishment endures even as specialists review the data again and talk about potential mistakes. There is undoubtedly something strange being seen via the telescope, and this has spurred discussions on whether modifications to the conventional cosmological framework are necessary. There are more than simply stars and galaxies in the universe. It functions somewhat like a time machine as well. Looking back billions of years in time is possible when one observes things that are billions of light years away. Astronomers are looking at more than just any ordinary photo, though, thanks to JWST. They are exploring the time periods immediately following the Big Bang, when hot, dense matter was generating the earliest structures. The conventional view, which was based on data from major ground-based observatories and devices like the Hubble Space Telescope, predicted that stars and galaxies would gradually accumulate over many hundreds of millions of years. However, JWST discovered evidence of brilliant, mature-looking galaxies that may have emerged as early as a few 100 million years ago. Many people now wonder if there was an unforeseen event that caused massive cosmic systems to expand faster than previously thought. There is a strong desire to explain these results. To explain the origins and development of the universe, astronomers have developed ideas including dark matter, dark energy, and cosmic inflation. These concepts have mostly withstood innumerable tests, from galaxy surveys to cosmic microwave background observations. However, open questions can take on new shapes every time a more potent tool is developed. Since the James Webb Space Telescope can detect details that previous observatories couldn't see thanks to its infrared vision, several of these questions have been reopened. Older hypotheses may be supported or refuted by new information, which might pave the way for more significant developments in the future. Currently, a large number of observers and thinkers concur that JWST is expanding our understanding. It is unlikely to completely alter our existing cosmic model, but it might point out places where we miscalculated the rate or timing of evolution. That in and of itself would be intriguing, since it would entail updating early structure formation timeframes and procedures. The ability to view star-forming areas at previously unattainable levels of detail, because to the telescope's reach, has also helped us understand how dust and gas condense to produce the first star clusters. It is also identifying clues that point to the existence of potential superlarge black holes and other mysteries that may be hiding at the beginning of time, as if that weren't enough. the possibility of a paradigm change. Although the notion of a paradigm change may seem extreme, astronomy has a track record of significant advancements. For centuries, people thought that Earth was the center of the universe, and it required discussions and observations to disprove that notion. We later discovered that the universe is expanding and that our galaxy is only one among billions. These changes are frequently fueled by improved measurements and new telescopes that reveal previously unknown information. This legacy is presently being carried on by the James Webb Space Telescope. We can view cosmic epochs that were previously only postulated because to its architecture. We may be forced to reevaluate our conventional theories if the evidence keeps pointing to galaxies that seem to originate too rapidly or exist in larger numbers than anticipated. The way matter clusters together in the early cosmos is one of the main areas that might alter. Researchers have worked for years to improve their calculations of how dark matter halos aid in the formation of galaxies. According to conventional wisdom, matter is progressively drawn into ordered structures by gravity, which then give rise to increasingly complex forms. This is not a quick procedure. Gas must cool and condense over time in order to form new stars. It was anticipated that each of these processes would take place in a predictable order. But according to some of the galaxies seen by JWST, star creation occurred quite quickly, rather than in the usual gradual burn that astronomers had expected. In addition to star formation, the amount of normal matter that pools into these early galaxies is also being examined more closely. Usually, just a small portion of the gas that is accessible becomes stars. However, a few recent findings suggest that gas may be used almost entirely. That is difficult to reconcile with conventional star formation models, which postulate that a large portion of the gas is prevented from forming stars all at once by processes like stellar winds, supernova blasts, and other feedback mechanisms. It may indicate that early galaxies had more effective methods than present galaxies for converting gas into stars if the telescope's data is reliable. According to certain theories, these early stars were so hot and massive that they eventually exploded in strong supernova explosions, rapidly introducing heavier elements into their environs. However, even that is only partially responsible for the rapid formation of large star clusters so soon after the Big Bang. The mass of these recently discovered galaxies is another factor to take into account. Some of them seem much too hefty for their position in the cosmic chronology based on the telescope's observations. The appearance of so many stars does not easily fit calculations about how much material may accumulate in a few 100 million years. The key question is whether dark matter or some other unidentified factor help to accelerate the accumulation of matter, if such things are supported by more data. Or are we misinterpreting red changes and perhaps judging their age and distance too much? Before making changes to basic ideas, scientists must confirm each piece of evidence to rule out less complex answers. However, the quantity of these strange objects continues to increase with each successive deep field shot, indicating that it may be a common occurrence rather than only an isolated anomaly. Experts continue to exercise caution during this discussion. Changes in paradigms take time, particularly in an area as data-driven as astronomy. However, the constant stream of perplexing data from JWST has raised important questions over whether minor adjustments to the lambda-CDM model are sufficient or whether new physics is hidden. Depending on who you ask, the term new physics might evoke either enthusiasm or skepticism. However, there is no denying the telescope's catalytic function. It has, at the very least, forced astronomers to re-examine the processes that lead from primordial gas to star-rich galaxies, forcing them to search for errors or omissions in their earlier process-based models. Important findings from the early cosmos. The discovery of what seemed to be galaxies from a period when the cosmos was only a few 100 million years old is one of JWST's most notable accomplishments. Although seeing early galaxies is always the goal, scientists just could not foresee the number or mass of these galaxies. Some appear to be so big that, assuming the age estimates are accurate, gravity could not have had enough time to collect so much material in one place. This suggests that either some underlying process accelerated the production of these structures, or that our conventional timescales for star formation and galaxy evolution need to be re-examined. In addition to galaxy formation, some of these early objects have been found to contain heavier elements than hydrogen and helium. Typically, heavier elements must be created during supernova explosions or fused in their cores by one or more star generations. If the galaxies from the very earliest era already exhibit these components, it indicates that stellar material was recycled quickly, or that the star formation process was far more extensive and intense than previously thought. We can see how quickly the Forpeth, we call it the galaxies, Rudisid, cosmic cradle of stars, began churning out heavier materials by using spectroscopy to observe these chemical signatures. The sheer diversity of forms is another. Early galaxies are thought by astronomers to mostly consist of tiny, asymmetrical star clusters. However, objects discovered by JWST appear strangely well structured, with arms or bulges resembling those of more developed galaxies. Such arrangement raises the possibility that collisions and mergers may have occurred on a timetable distinct from that predicted by earlier theories, or that some gravitational processes operated quickly. In instance, mergers can accelerate star formation by compressing gas clouds and producing shock waves. However, the early microhalos were not anticipated to create such remarkably vast and luminous systems, even when merging was taken into account. Naturally, every new finding prompts more observations meant to confirm distance estimations using more precise spectroscopy. Redshift measurements are useful for placing things in time, but they can be challenging to make accurate for very faint sources. The bulk and age of these sources may not be as shocking if they are, in fact, closer than we realize. However, as more spectral lines, which resemble cosmic fingerprints of the distance traveled by light, are collected, scientists are becoming more certain of their redshift findings. The conflict with conventional theories only gets worse if these lines demonstrate that these galaxies actually existed only a few 100 million years after the Big Bang. However, it is not only about galaxies. Additionally, JWST has detected signals that might point to massive black holes in the early cosmos. The amount of material that black holes may consume is directly related to their development rate. Furthermore, it is often believed that the earliest big stars collapse to generate tiny black holes. They become extremely big black holes by merging or consuming material over billions of years. At a very young cosmic age, it would be puzzling if we discovered galaxy cores with black holes that were 1 million or perhaps 1 billion times the mass of our Sun. These things may have developed in a completely different manner, suggesting a distinct line of cosmic history from the one we have previously thought about. Unexpected structure and star formation. The possibility that some galaxies in the early cosmos converted almost all of their gas into stars is a significant finding from JWST. It was once believed that only a tiny percentage of a galaxy's available gas would ever become stars, with the majority either remaining in gas clouds or being destroyed by supernova explosions. However, if JWS data is reliable, we could be witnessing a sort of uncontrollable star-forming activity that nearly entirely transformed gas into stars. Almost all star formation models that rely on moderating factors to stop a single wave of all-out collapse are called into question by that theory. How such a procedure may take place is the key question. One theory is that star formation took a different course than what we observe now due to the harsh circumstances of the early cosmos, when gas was denser and radiation fields were stronger. Perhaps normal matter was more effectively drawn in by the existence of dark matter halos, causing everything to collapse swiftly once the gas cooled sufficiently. Another theory is that early gas clouds were able to form more easily because of differing magnetic fields or turbulence than those found now. Although they still need a comprehensive explanation, Astronomers are investigating these avenues in an effort to explain the unexpected star formation rates suggested by JWST data. Structure is also important. Large spiral or elliptical galaxies were thought to be the result of several mergers and billions of years of gradual formation. However, certain objects in JWST photos already exhibit unique structural characteristics. Verification of that suggests that organization into a disk or central bulge may occur far more quickly than previously thought. There is a distinction in science between an unexpected finding that calls into question a theory's more specific elements and one that calls into doubt the theory's basic chronology. These early organized galaxies are among the most striking findings, since many people believe they belong to the second type. Verifying these statements practically can be accomplished using thorough spectroscopic surveys. We may determine the relative abundances of specific elements, calculate the speeds at which stars develop, and search for signs of black holes or supernova remnants when we record a galaxy spectrum. In an effort to validate or refute the existence of anomalous masses, chemical signatures, and star birth histories in these galaxies, teams are now use JWST. It will be easier to determine if these tendencies apply to a small number of uncommon things or are more general with more. Data. The discussion concerning altering cosmic timelines will pick up considerably more steam if they become widely accepted. The notion that certain objects may not even be galaxies, at least not in the conventional sense, adds to the excitement. Could strangely bright events or unusual star clusters exist that resemble the measurements we anticipate from galaxies? Every applicant is being closely examined by researchers who are comparing data from various equipment. If there is anything strange in the early universe, we have a good chance of finding it or at least identifying enough hints to suspect it exists because to the enormous quantity of information JWST can collect. This indicates that there are other aspects of star creation being examined. The whole theory underlying the large-scale organization of matter is being examined. New conflicts with the conventional approach. The lambda-CDM model has long offered a straightforward yet useful summary of how the universe functions. It postulates that dark matter, which interacts gravitationally but not electromagnetically, contributes to the formation of the framework that galaxies are built upon. In contrast, dark energy accelerates the expansion of space. Once the correct numbers are entered, the majority of observable events, ranging from galaxy clustering to the cosmic microwave background, fit inside this picture. However, there were significant conflicts even prior to JWST, such as the discrepancy in measurements of the rate of cosmic expansion and the Hubble constant. These tensions might develop into larger fissures when local observations using the Webb telescope reveal more oddities than early universe data. If JWST continues to catalog a significant number of galaxies that are just unable to develop on typical lambda-CDM timescales, these fissures may become apparent. The hypothesis may need to change to account for an earlier or more intensive epoch of star formation and matter clumping if confirming their mass and distance is accurate. This may include changing the characteristics of dark matter or introducing an additional stage to cosmic development. Sometimes little adjustments are sufficient, such as modifying the rate at which dark matter particles may cluster together. At other times, more significant adjustments are required, such as taking more physics into account during inflation. Theories may also change in the area of dark energy. Dark energy is now thought of as a continuous force propelling faster growth. On the other hand, the speed at which structures evolved would have been temporarily impacted if the early cosmos had a different kind of energy field. Although astronomers are not sure if the evidence will lead them in that direction, there is a possibility because JWST data consistently points to a faster rate of cosmic evolution than is implied by mainstream theories. In several respects, it is a conundrum that necessitates considering numerous factors simultaneously. The mass distribution, the total amount of normal matter, the pace of star formation, and the expansion timeline. Advanced simulations that compare JWST's observations with the theoretical predictions probably going to provide confirmation. Numerous research teams worldwide are currently attempting to replicate the earliest galaxies using conventional assumptions in order to determine whether or not the new data agrees with them. In the event that they don't, the next stage is to modify variables such as the quantity of dark matter, the pace of star formation, or the rates of gas cooling to see whether the findings are more in line with what JWST is revealing. This approach is methodical yet slow, and it may help identify the component of the puzzle that is most accountable for the differences. Even though it was formerly believed that tiny galaxy collisions took a long time, it's likely that early universe circumstances accelerated the process. It's possible that high-density areas quickly collapsed into massive systems, accelerating star formation and causing early chemical enrichment. However, a significant change from previous estimates would be necessary for it to occur frequently enough to explain the numbers we observe. It is still unclear if that change can be made using the present standard model or if something completely different is needed. In any case, the tensions are genuine and contribute to the excitement around dark matter, potential explanations, and fresh JWST data releases in the astronomy community. Astronomers naturally question if we have misinterpreted the behavior of dark matter or dark energy when presented with findings that defy assumptions. The main way that dark matter shapes the creation of galaxies from an otherwise dispersed dispersion of gas is through its gravitational attraction on visible matter. According to the conventional model, structures can develop over long periods of time because dark matter is thought to be relatively cold and its particles travel more slowly. Perhaps dark matter was not as cold as we believed or behaved differently under the particular circumstances of the earliest cosmos if early galaxies are more massive or abundant than we anticipated. Another theory is that the dark energy responsible for space's rapid expansion did not always behave in this manner. Theorists usually regard it as a constant characteristic that has dominated the cosmos throughout cosmic history. Could it be that in the past there was a more dramatic temporary variation in dark energy which accelerated the formation of structures before ramping back up? Although that theory is not widely accepted, JWST's surprising discoveries could spark fresh ideas about time-varying dark energy or other inventive adjustments that would enable the rapid appearance of massive galaxies. Then there's the theory that the Big Bang timeframe itself may require minor revisions. The cosmos may be older than we realize. Or perhaps star creation occurred in bursts that defied easier estimates throughout the first few 100 million years. The present age of 13.8 billion years is supported by several lines of evidence, ranging from distant supernova observations to the cosmic microwave background, which makes some astrophysicists wary of this method. A mound of facts that supports this age would need to be addressed in order to change it. Smaller changes to our understanding of that period are still possible, but a complete reset of the cosmic clock is improbable. The theory that primordial black holes might have emerged immediately following the Big Bang has also been put forth. Theoretically, these black holes might accelerate the formation of early galaxies or seed them. Superhuge black holes might have contributed to the faster-than-normal suck-in of gas if they were existent. That could account for some of the events observed by JWST in big galaxies. However, it is difficult to demonstrate that such black holes truly developed at those early stages. The community has not come to an agreement on it, and it would require extremely particular circumstances during inflation or the immediate post-inflation period. However, the data from the Webb telescope may ultimately compel a more thorough examination of all these options, particularly if more straightforward explanations are unable to reconcile the mounting corpus of observations. Astronomy's future with JWST. It is evident that JWST is only starting to establish itself, despite the uncertainty and potential conflicts. As long as its equipment and orbit stay steady, the telescope should last for many years. This implies that a steady stream of pictures and spectra is to be expected. Astronomers will eventually have a better understanding of how star clusters respond to strong gravitational fields, how galaxies develop in the early stages of cosmic history, and whether or not black holes have evolved swiftly. Future ground-based and space-based mission design will also be guided by JWST data as scientists pinpoint particular phenomena that require further investigation. For starters, astronomers are putting up plans to utilize JWST in conjunction with massive ground-based telescopes or to see even fainter objects. Advanced spectrographs on Earth that use certain lines in the spectrum to verify redshifts and compositions are one example of this cooperation. By eliminating biases or illusions that could have resulted from insufficient data, the synergy has the potential to improve each discovery. The signals become more credible if they are observed by several observatories, increasing the likelihood that modifications to cosmic theories are required. Additionally, astronomy's social aspect is also being impacted. Large worldwide teams work to create JWST, and much larger teams are required to analyze its data. To interpret the results, researchers from a variety of disciplines, including star physics, galaxy evolution, and cosmology, are collaborating. Because of this collaborative culture, both theoretical models and actual observations are used to study complicated challenges like high-efficiency star formation. In order to avoid filling one gap by making another, everyone is attempting to put together a coherent narrative. We could potentially see more telescopes in the future that are focused on certain jobs that JWST is not very good at, like high-resolution mapping of large swaths of the sky. JWST does not simultaneously cover large fields, but it is excellent at doing in-depth, comprehensive studies of smaller areas. JWST's limited but extremely deep focus may be complemented by missions like the soon-to-be-launched Nancy Grace Roman Space Telescope, which will scan vast swaths of the sky. When combined, these resources might provide a more impartial view of the galaxy web. They will determine the relative rarity and frequency of these big or early galaxies in the universe, the diversity and diverse, the infrequency of the universe. This astronomy community will be alert due to JWST's constant data releases. Every new deep field or spectroscopic study has the potential to challenge presumptions regarding black hole growth, star cluster formation, gas cooling rates, and stellar lifespans. Additionally, it's possible that the stellar populations in the first galaxies were very different from those we observe now, with stars achieving either shorter or more extreme masses or lifespans. If this is the case, we may find chemical hints in their starlight, such as odd carbon or oxygen ratios, that might indicate unique nuclear activities occurring deep within. The early universe may have been more active than our typical mental images indicate, since it would be another indication that nature had several ways to create stars in the early stages of the cosmos. Beyond studying galaxies and black holes, JWST may also be used to analyze the atmospheres of exoplanets. That subject illustrates the telescope's wide range of capabilities, even though it has nothing to do with the construction of huge structures. We may be able to identify chemicals like carbon dioxide, methane, or water vapor by examining the spectrum of light traveling through the atmosphere of an exoplanet. That may lead to the discovery of potentially habitable planets. It is yet another factor contributing to JWST's popularity. It explores both the distant past and the possibility of extraterrestrial life. We appreciate you seeing another episode. For higher quality material, click the video on your screen while you're still here.